Okay. Since you know who I am and you know how I operate, I'm all about protocols, not putting the proverbial cart before the horse. That being said, tonight, one night and one night only, we're going to put the cart before the horse. The way that I want you to approach ELEC 110, and this is a recipe for success, because like I said, I've been doing this for a couple of years. I know what works and I know what doesn't. And I guarantee you, if you follow the syllabus, if you do all the assignments that you're given, if you follow that recipe for success, you will be successful. You'll pass this class. Guarantee it. I don't know if any of you also know, Lake Washington Technical College has a guarantee that if you graduate our program, go into industry, and your local, whoever you go to work for says you don't know what you're talking about, we will re-educate you for free to get you to the standard that industry says. You know, how many students have been sent back to the electronics program? Zero. So I know it's working. So keep in mind the way that this is supposed to work. I think this really is the best recipe for success. Is I like to read through the chapter very quickly. And what that does is like formats your hard drive for what you're about to receive. That, of course, is a given that you've already reviewed the syllabus. In reviewing the syllabus, that shows you specifically, like on page 1 they start, the course outcomes and objectives. And then you look at how those course outcomes and objectives of the syllabus, which is really the training contract between you and I, how closely the book and the chapter works meet those objectives. So read through the objectives in the syllabus first, then read through chapter 1 or chapter 17, whatever chapter you're on, just like a book. But this isn't a book, it's a textbook. So when you get to the end, it's not going to be like, oh, I never knew it was going to turn out like that, okay? I mean, it's a textbook. It's a text/reference book. After you've read through the chapter, then go through it with a fine-tooth comb. Whenever you come to an example or a problem, take out your calculator and do the math. And follow along and do every practice problem. Keep note of that because that's going to be part of your written assignment. Then when you're all done with the chapter, then I'd read through it again very, very quickly, just to make sure you retained all that information. Some of the stuff that we're going to talk about tonight in chapter 1, like atoms, molecules, you probably have heard before, right? The periodic table. A lot of you have heard that already before. So keep that in mind that if you're going through the book and the book is talking about stuff that you already know, you don't need to beat that to death. And that's actually good because it's going to draw you to focus your attention on those areas that you don't understand. And you're going to be able to dump all of your energy into the stuff you don't understand. Does that make sense? I mean, it sounds really basic when you think about it like that, but that's really what's going to be the most effective means of traversing this. Normally, I will not lecture on a chapter until you've read the chapter, done your homework, and gotten together in your teams and completed a peer review, right, of your homework. Once your homework has gone through that process, and then you've got completed homework, then come into lecture, because you know what I want to spend my time in lecturing on? What you didn't get out of the book, what you didn't get out of the assignments. That's how I want to spend the majority of my time in a lecture. Fair enough? Okay. Let's get started. These slides here actually follow the book. And these slides, by the way, are available online on the Google site. The TAs helped you out on how to get that site. The links are right there in your syllabus. So what you could do is you could download these from the site to your computer and then put them on your laptop or home computer and have the same slides that I'm showing you tonight. Also, there are audio files of this lecture in MP3 format that you could download. Joe Grenick on MP3. Right? And listen to me when you're working out at the gym or running from the police or whatever it is you do when you listen to MP3s. And then also we're going to be adding to this now videotape of the lecture that we've got our TAs back there working on right now. So ultimately we'll be able to upload that. And the reason that I go out of my way with recordings, with the slides, I've got nothing to hide. I've got nothing to hide. As a matter of fact, I want to give you as much information as I possibly can so that you could benefit from that information. And you know what? How many of you here own any DVDs? Your favorite movies? Why would you own a copy of a movie? Why would you do that? Isn't seeing it once good enough? Why would you go out and buy DVDs of a movie? Because they're cheap. Unless they're giving it away, so it costs money. Why do you? What's that?
Because you couldn't bid for it, that specific one?
Yeah.
You can watch it anytime you want.
You can watch it anytime you want, but why specifically would you purchase a particular movie?
Because it encompasses your interest.
Exactly. It encompasses your interest. And for those of you that have movies, how many of you have watched the movie the second time and picked up stuff out of it the second time around? That there's some movies I've seen in the theater that I'm like, I got to go out and get that DVD because I want to see this again. I know how it ends up, but I want to see it because I missed something in the beginning and I want to look for that thing that I missed in the beginning or whatever. So it's perfectly natural for you to want to hear this lecture over and over again. I mean, for some of you, once might be good enough. Okay? I go to church on Sunday. My pastor, normally, he gets up there and he preaches. I get it right the first time. I don't need to hear it again. Okay? For some other people, though, and actually at my church they do audio recordings, and then people can listen to that content. They want to hear it again. Normally I get it the first time. That's the kind of guy that I am. That's the type of learner that I am. But look at that. That's the other thing, too, with taking notes. Some of you, it's been a while since you've been in school. Try to hone your note-taking skills. When I emphasize something, I'm usually emphasizing it for a reason, and that reason is you may see it again in the future on a quiz, on an exam, but most importantly, you may see it in industry. Because one of the things I don't want to do is teach you the exam, teach you the quiz. That's not what it's all about. One of the things that I want to share with you is I'm not really concerned. I mean, I want all of you to pass my quizzes. I want you to all pass my exam. I want you to all pass this class. But to be totally honest with you, do you know how I measure your success? I measure your success as to where are you going to be 5 years from now. And did I give you anything out of this course that helps you in that position you're in 5 years, in 10 years? The payoff for me is when you call me and say, Joe, I'm in town or I'm passing through. I'd like to buy you lunch. I like lunch, okay? Swing by, buy me lunch. Tell me what's going on. Tell me what you're doing now and how I had an impact on that. I actually, I went on a cruise over spring break, Caribbean. I was just getting ready to get on the ship, and I get all my emails forwarded to my phone, and I got an email from a student that I had in 1993. And he introduced himself, and he says, I don't know if you remember me. You know, my response back to him, of course I remember you, you know, because again, we established a relationship, a professional relationship. But he graduated, he went down to California, kind of dropped off the radar. He was going to be in the area and was wondering if I'd be available next Friday to get together and we could visit. And I said, yeah, geez, unfortunately, I'm out of town. And, you know, but you know, that is how I measured the success. Number one, that he remembered me. Number two, what he learned here is part of his present reality. So that's what I want all of you to think about. Yeah, you want to pass the quiz, you want to pass the exam, you want to pass the class, but where are you really going to use this stuff? Anyway, kicking things off here, this is section 1 of the book. Section 1 of the book, area of the text that deals with what are called DC circuits. DC stands for direct current, and we're going to talk about the difference between direct current and alternating current throughout this. Chapter 1 deals with the fundamentals of electricity. And I got to tell you that these first few chapters are like sacred chapters. You know, we should like ring bells, and like hit gongs and chimes or whatever when we speak of some of this stuff. Because if you want to be successful in electricity and electronics, these things that we're going to speak of are critical attributes of what makes stuff work. As far as I'm concerned, I'm going to let the cat out of the bag from the get-go. Okay? The big four things that we're looking at that drive this entire industry are four properties. The properties are voltage, current, resistance, and power. Voltage, current, resistance, and power. Voltage, current, resistance, and power. My cell phone works because of voltage, current, resistance, and power. My car computer works because of voltage, current, resistance, and power. Satellite TV works because of voltage, current, resistance, and power. Anything electrical or electronic works because of those four. So what we really need to ensure is that these four properties that we're going to discuss, we fully understand up one side and down the other. As I said earlier, I've been doing this like since puberty. So you would think that I know everything there is to know about voltage, current, resistance, power. No, I do not. Occasionally I get questions from students that are associated with those properties that I can't quite answer, even though I've been doing this for so long. So I'm on a continual journey to learn as much as I can about those four properties. So we're going to kick things off with Chapter 1 here, dealing with the fundamentals of electricity, but pay special attention to those four properties: voltage, current, resistance, and power. The big four. I like to call them the big four because they are the big four. It's what everything is based on. If you know what's going on with voltage, current, resistance, and power, you know what's going on inside the circuit. We're going to talk about that. So kicking things off, fundamentals of electricity. One of the things that I do at the start of every lecture is I review the objectives. The objectives that I review are the same objectives that are on the syllabus. That's a pretty good reason why I selected this textbook to use. Although there's errors in this textbook, although it's not the best textbook on the face of the planet, the objectives in the textbook reflect the objectives in the syllabus. One of the other things I want you to fully understand is I don't teach the textbook. I teach the curriculum. The curriculum is contained in the syllabus. The curriculum is derived through input from our local industry advisory committee. This is a group of volunteers that get together on a regular basis, sit down, and tell us what we need to be doing for this program to stay competitive. So this book works really good because you're going to do all the chapters in it. But occasionally, in the future, you may get some textbooks that the instructor is going to say, you don't need to do this chapter. Why? It's not part of the curriculum. Local industry really doesn't think it's important that you learn that aspect of it. So does that make sense? Okay. One of the reasons that I review the objectives as well is to prepare you for what you're about to receive. It's like formatting your hard drive so that when I start talking about this stuff, you're kind of like ready to store that information away on your hard drive, your mental hard drive, your brain. So let's take a look at this here. Objectives: after completing this chapter, the student will be able to define matter, element, and molecule. There's 3 questions right off the quiz. Define matter, define element, define molecule. It's an objective. I hope at the end of this chapter you could define those. List the parts of an atom, define the valence shell of an atom, and identify the unit for measuring current. Draw the symbol used to represent current flow in a circuit. Describe the difference between conductors and insulators and semiconductors. Define difference of potential, electromotive force, and voltage. Voltage, wasn't that one of the big 4? So again, if this was like church, you'd be ringing bells or gong, you know. We'll talk about projects later. Some of you may want to build sound effects so that we could, you know, whenever do that stuff. Or dim the lights. Voltage. Draw the symbol used to represent voltage. Identify the unit used to measure voltage. Define resistance. Gong. One of the big 4. Identify characteristics of resistance. Gong. in a circuit. Identify the unit for measuring resistance and draw the symbol used to represent resistance in a circuit. Everything you are about to learn as it pertains to electricity and electronics is traceable back to matter. Do any of you here know anything about matter? Do you know what matters? Matter is anything that occupies space and has weight. Does anybody know where we could find the absence of matter? Does anybody know, can we create this condition here on planet Earth? Vacuum. And I'm not talking about the Oreck 5-pound upright. I don't think that's what you're talking about, right? What kind of vacuum are you talking about? It's called industrial vacuum. And in essence, what we're talking about is pumping all of the matter out of a vessel so that all that's left inside is space, empty space. It's used a lot. A lot of you that go into high-tech careers, you're going to see this process used in the manufacturing process because it allows us to only put into the chamber what we want to be into the chamber. Where can we find a large abundance of an absence of matter? Space. And you know the odd thing about it is that's why it's called space. Because there's no matter. There's no matter. Now, if you're in a space ship traveling through space and you roll the window down and you stick your butterfly net out and you pick up some cosmic debris in your butterfly net, pretty odd thing to do. Don a spacesuit if you're going to roll the window down to the spaceship, do that. But if you find any cosmic debris in your net, that means that you have found matter. Because if it's something and it occupies space and it has weight, therefore it's matter. Have any of you heard of antimatter? We will not be talking about that here in this program. Okay? I used to think it was science fiction until I was talking about it in a lecture like this, and I had a student raise their hand, and we're not going to talk about it because I don't know anything, the absence of matter, antimatter, the opposite of matter. And he brought in an article the next week about a NASA project. And these NASA teams are all about funding. So all these PhDs and all these scientists, it's all about getting money for them to continue their research. Well, NASA was running out of money, and there was a particular group that was doing research. And they were going to get their operation shut down. So as soon as they all were basically put on notice, you all are no longer going to have a job at NASA. They're like, oh, jeez, that's too bad, that's really bad. Well, why is it so bad? Well, we just discovered a cloud of antimatter, and we think it's headed this way. So right away, NASA gives them more money to continue the research. And somewhere in my archives, I've actually got a picture of this antimatter cloud that, who knows if it even exists. But obviously, if antimatter collides with matter, they cancel each other out. So if there was antimatter cloud that inundated our solar system, we'd be gone. I don't know where we'd go, but this is what they say. Enough said, we won't be talking about antimatter in this class. We're more concerned about matter. Now, the basic building block of all matter that we're aware of, and this is really interesting, is what's known as an element. An element can be found on the periodic table. I must not be a real professor. If I was a real professor, I'd have one of those pull-down charts that's got the periodic table and all the squares, That's the sign of a true professor. I don't have one of those. I could probably call it up on my computer screen, but it wouldn't be the same of having one of those pull-down charts where you could, with the pointer, right? And you've all seen that. You all know what I'm talking about, right? Probably saw it back in elementary school. Elements of the basic building block of nature cannot be reduced to a simpler substance by chemical means. And believe it or not, there are only about 100 known elements in existence, period. Over 100 known elements, period. That means me, you, that desktop, the chair, a cow, a monkey, a sports car, an airplane, we're all made up of 100 of the same ingredients, period. Isn't that amazing? That was one of the things they really didn't know about going to the moon. Were they going to go to the moon and find some new element? They went to the moon and they found the same stuff we got here on Earth. So basically the assumption is in the scientific community that really the entire universe is made up of about 100 of the same ingredients. I mean, I got more crap in my pantry at home. Spices, seasonings, I got all kinds of stuff all over the place. But the fundamental essence of it all, 100 plus elements, period. Everything's made up of those same 100 plus ingredients. Now, we're really focused on the parts of an atom. So when we have an element, the smallest particle that we could break that element down into and have it retain its identity is an atom. So I know you think I'm going all wacky like chemistry on you and everything, okay? Bear with me. We have to understand the essence of matter so that we can get electricity out of matter. That's where we're going with this. The first part of the atom you need to understand is called the nucleus. And the nucleus is not even really a part. I misspoke that. It's not a part, it's a place. And that place is simply the center of the atom. The first true subatomic particle that we're going to talk about is the proton. Proton is a positively charged particle that's located in the nucleus. Okay? And I just said something that's very, very significant. I just said the word positively charged. For the first time in this program, we just spoke of something that has an electrical characteristic, a positive charge. So a proton has a positive charge. The other subatomic particle that's located in the nucleus of an atom is called the neutron. And neutrons are uncharged particles, meaning no charge. One of the ways that I remember it always is proton, proton, positively charged. Both start with the letter P. Neutron, neutrally charged. Okay? They're not positive or negative. They're uncharged. They're neutrally charged. That's why they're called neutrons. Electrons, well, that's the other subatomic particle. And if one's charged positive and one is neutral, then therefore the electron must be negatively charged particles. The electron actually orbits the nucleus, where the protons and the neutrons are located. This is a very, very significant slide. Remember earlier I shared with you a little bit about my background. I wasn't the sharpest tool in the shed. And as a matter of fact, when I was in the Navy on active duty, my uniform, the Navy, even if you sail on a cruise ship, you have a symbol that identifies what division you're part of. And for me, I had on my arm my chevrons, that signified, my rank. But then I had a helium atom on my arm. And that helium atom was to signify matter. And the helium atom with the electron orbiting around the outside was to signify electrons orbiting the nucleus. Why? Because I was an electronic technician. And I basically went for like 3 years of my career before I realized, why is there like an atom on my arm? Okay, what does that mean? What it means is the electrons orbiting the nucleus because I was a subject matter expert, a technician on the behavior of electrons. That's what you're all here to learn. If you're here to learn about electronics, you're here to study the behavior of the electron. And that's what we're really going to talk about. Make sense? One of the things I do not want you to study while you're here in this program, and I'm pretty open-minded. If you want to go off and do some projects and stuff like that, I'm all about it. One of the things I really don't want you doing is anything with the nucleus of the atom. Okay? And if you plan on doing anything with the nucleus of the atom, give me fair warning. And I think I'll stay in Federal Way that day. Okay? And then you could have at it and try to split the atom or do whatever it is you're going to do. But when you start playing around with the nucleus of the atom, bad things happen. As electronics professionals, we're only going to play around with electrons. As a matter of fact, we're only going to play around with certain electrons. And I'm going to share those electrons, what those electrons are with you in a moment. This is kind of sort of what it looks like, maybe. This is an artist's depiction, and the scale is really, really off. The proton is a very big particle. The neutron is a very big particle. So the nucleus, this is kind of working. Okay, this is kind of working for me. The electron, though, is not the same physical size as the proton. The electron would be like the spot of my laser pointer. But in actuality, if this truly was the neutron and the proton, I don't think this spot of my laser pointer would even be in the room anymore. That's how far the orbit is around the nucleus. I heard it once explained as like a cathedral. If you had the size of a grapefruit in the center of the cathedral, the electrons orbiting would actually be like on the outer walls. It'd be really, really far out there. So the scales here are off, but this gives you an idea what's going on. One thing I want you to understand also is that all matter, when in its neutral, natural state, has an equal number of protons and electrons. Protons are positively charged, electrons are negatively charged. They're equal number, so they cancel each other out. That means that matter is in a neutral, natural state. Did that answer your question? You got a
Balanced.
balanced.
Right.
So there's an equal number of electrons and protons in atoms until we do something to it. We're going to talk about that in a minute too, because we're not just going to let everything stay in a neutral, natural state. If we did, we'd be out of jobs. We wouldn't have current flow. It'd be a drag. A couple of the numbers that you need to familiarize yourself with. And one of the things that I want to stress to you is that all of you are here taking electronics courses. You're here to learn the language of electricity and electronics. That's really what it is. This is like taking a second language. I've actually had a lot of students that speak different languages, and English is a second language, and they wonder if they could come in and do it. It's like, yeah, you could come in and do it. Because you know what? What I'm talking about here is another language. So one of the technical terms that we may use in the future is a number called atomic number. An atomic number simply is the number of protons in the nucleus of the atom. And every one of those 100+ elements that I talked to you about earlier has a unique number of protons. You don't have two different elements that have the same number of protons. So the scientific community embraced this, and they said, you know what? Why don't we just use the number of protons, and that's going to give it its position on the periodic table. Make sense? Okay. The next number I want you to familiarize yourself with is the atomic weight. And the atomic weight deals with the mass of the atom, its weight, its physical weight. And remember when I said that protons and neutrons were big and they were contained in the nucleus? And the electron was just like a little tiny subatomic particle orbiting way outside? Basically, to end up with atomic weight, all you do is count up the total number of protons and neutrons in the nucleus. Count that up, that gives you the atomic weight. Every weight of every element on the periodic table is unique. And basically, the mass of the electron is so insignificant, we don't even take that into account in determining the atomic weight. Make sense? Now this is where things get interesting. First term, shell. This isn't the kind of shell you find by the seashore. What we're talking about here for shells is simply an orbital path around the nucleus. This is where the electrons orbit. They form concentric circles around the nucleus, and they're filled in sequence. Have any of you here been to a parking garage, like down at SeaTac Airport or Bellevue Square, or, you know, I don't know about you, and I'm, again, not the smartest guy, but normally I want to park at like the first level like I find a space at. So what I'll do is I'll go to the first level and I'll drive around, and if I can't find a parking space, where do I go? Up to the next level, okay? And then I drive around, and if I can't find a space there, where do I go? The next level, and I keep doing that. This is how shells are filled in atomic structure. When the first shell gets filled, then electrons start going out to the second shell, and then the next shell, and then the next shell. So our most complex atoms in existence have electrons in shells that are way out there because they have the highest number of electrons. And the higher the number of electrons, the higher the number of protons, because remember, they have to be equal. Make sense? Now, the shell that should most concern you is this valence shell. This is the outermost shell. If it's a complex atom, it may be way out there. If it's a simple atom, it's going to be real close to the nucleus. And I'll talk to you in a minute why it's important for two different reasons. The number of electrons contained in the valence shell also refers to the term valence. Now, this is the scheme that they came up with in naming the shells. If we have a simple atom, let's say we've got an atom that contains one electron. That one electron is going to be parked in the lowest level. And we're not going to call it the lowest level. No, that'd be too easy. We're not going to park it in what's called the first shell, because that would be too easy. You're here to attend college, okay, to get educated. So we've got to not call this the first shell or the A shell. We're going to call this innermost shell the K shell. Why? I don't know. It helps us educated people justify our existence. After the K shell comes this is the part that actually makes sense to me. After K comes L, M, N, O, P, Q. So I did okay with the alphabet. So it kind of makes sense. So what this means is the Q shell, the most complex element that we have found in the universe, contains electrons in the Q shell. Does that make sense? If it's a simpler element, an element with a lower atomic number, that means it's going to have electrons maybe only in some of these shells. But we have to fill a sequence first, fill this K shell, before we bump an electron up into the L shell, when L gets filled. And some of you that have maybe taken chemistry and some physics classes know there's a certain number. I don't want you to memorize that. That's not going to help you become an electronics professional. But just remember there is a limit of how many electrons you could park in a shell before the electrons have to go into the outer shell. Now, why am I talking to you about all of this stuff? Again, this was a question that plagued me for about 3 years since I was educated. Like, why were they teaching me about all the subatomic stuff? I'm not going to be some mad scientist, you know. Why do I need to know about the periodic table? Why do I need to know about subatomic structure? You know, I want to learn how to use a multimeter to take voltage readings. I want to know how to use an oscilloscope to take readings. Why do I have to understand subatomic structure? 2 reasons you need to understand subatomic structure. Number one is so you could identify the properties of materials that we use in electronics. That's first and foremost. Secondly, you need to understand where voltage comes from. We're going to talk about that in a minute. First, let's talk about some of these materials and their properties. Conductors. How many of you are familiar with conductors? Conductors. That's the guy that runs the train, right? Is that the conductor? I actually saw that the other night. What's that movie? Unstoppable? How many of you have seen the movie Unstoppable? Train? It was actually a pretty good movie. You haven't seen that one? Yeah, it was good, wasn't it? Train, running out of control. Based on true stories. It was based on a true story, you know. Let's set the throttle and jump off the train and switch the track and jump back on it. You know, it just didn't work out very well. Anyway, well, that's not even what we're talking about. Conductors, we're not talking about train conductors. We're talking about conductors, electrical conductors. Materials that readily accept the flow of electrons or electricity, if you will. Categorically, the textbook says they're materials that contain a large number of free electrons. However, I want you to think of it in a different way. When I speak of conductors, I am speaking of materials that have 3 or fewer electrons in the valence shell. And by the way, in this class, in this program, the only shell that you will ever work with, for safety reasons, is the valence shell. If you plan to experiment beyond the valence shell, again, let me know, and I'll probably stay home that day. Okay? So it's only the valence shell. So if you've got an element that has 3 or fewer electrons in the valence shell, it's going to potentially be a good conductor. Now, in order of precedence, the material that has the best conductivity or conductance is that of silver. Silver, believe it or not, that's the best found in nature. Out of all the elements, silver is the best. Followed by copper, gold, aluminum, tungsten, iron, nichrome. Okay? Silver is the best. If silver is the best, why when you buy a stereo, why when you buy audio-video equipment, do they try to sell you gold-plated patch cords? Okay, we've got one response there, money, yeah. They can get more money out of you.
It's corrosion. Silver has a higher corrosive potential than gold.
Absolutely. Absolutely.
And copper is a little bit more corrosive than gold, but not as much as silver.
So basically, gold is the least likely to oxidize and corrode. So when we get copper wire and plate it with gold, we get a good conductor, because gold is still a good conductor, but it won't oxidize. If you're scuba diving in the Caribbean and you find a treasure chest full of gold that's been sunken hundreds of years underwater, and you dig it out of the sand and you open it up, underwater, salt water, hundreds of years, you open it up, you would know that you found gold, because it would look as good as the day that that treasure chest fell off the pirate ship. If you found a treasure chest under the ocean in the Caribbean and it was filled with silver and you pried it open, you'd be like, oh, what happened in there? Because it's all oxidized. Of course, there's still good silver in there, but the exterior would be oxidized. So that is why we use gold-plated connectors. Don't oxidize. We live in an oxygen-rich environment. So if I could have gold-plated connector to connector and I could mate the two, I'm going to get the best possible electrical connection that I can. Now, do you really need to go out and buy those gold-plated audio-video connectors? It's actually kind of funny because I've seen a lot of people go out and spend good money on those, and then they plug it into the back of a dusty amplifier. You know, it would have been better for you to go out and get some technical grade alcohol, clean the male-female connectors, you know, connect them, and you'd get a better electrical connection. Now, in a perfect world, a totally clean gold to totally clean gold, clean, nice, no dust, is going to give you a superior connection. We actually learned a lot of this was developed in the space program. Because think about it, to basically send people to the moon and have them get back and have those electronic circuits work, needed to be highly reliable. So this is where NASA started playing around with everything is interconnected. You can't permanently wire everything up. You have to have boards and sockets, and everything is interconnected like that. So NASA did a lot of research, and they said, hey, we plate the stuff with gold. We'll be golden, you know. Literally, that started that whole trend in electronics. A lot of the circuit boards and stuff that you buy, your computer motherboard, you know, your video card have gold plating on it, so they make that connection, and it's a highly reliable connection. Big thing I want you to remember, though, 3 or fewer electrons in a valence shell. Insulators are materials that prevent the flow of electricity. The textbook says they're stabilized by absorbing valence electrons. The material found on planet Earth that has the highest insulative quality in nature is mica. Any of you know what mica is? It's found in rock formations. It's very fragile. It's a good thermal insulator, and it's a good electrical insulator. A lot of times it's found in quartz formations. And it's almost like paper, like you can kind of peel. There's one layer and another layer and another layer, but it's highly fragile. That, for thickness, is the best insulator that we have found in nature. That's why it's at the top of the list. That's what we compare everything to. Glass is high, but not as high as mica, followed by Teflon, paper, wax paper, which is used in the manufacturing of some electronic components. Rubber, Bakelite. You know what Bakelite is? Bakelite is like the handle on your toaster oven, and like when you drop it, it chips it and you can't glue it back together. It's not only a good electrical insulator, it's a good thermal insulator. It's that black stuff that, again, you chip on your pots and pans and you can't fix.
Wasn't that the original form of plastic? They started mass
Yes. Yeah, it is one of the original forms of plastic, if you will, that they used as a composite, if you will. Oils, a lot of oils are used. They used to use a lot of oils that had a lot of poison in them for like electrical transformers, but we kind of got out of that because oil is an insulator. And it's nice because oil will draw heat away from circuits. So if you had a circuit submerged in oil, if any what do you call them, computer heads here, PC files, you know, one of the big problems we know with PCs are heat, the generation of heat in the processing. So one of the big things is if you could super cool a computer, you get more performance out of that computer. So if we got the computer, don't try it again with my computers, but if we got it and submerged it into a vat of oil and then we cooled the oil and recirculated it, we could draw more heat away from the circuit, and then we could start bumping up the speed of the computer and in the industry overdrive the chip. Ask more of the chip than what it's rated for. Yep. Porcelain. And of course air. Air is an insulator, isn't it? If you've driven under power lines, what's between the power lines? Air. I don't know if you've ever driven under or walked, do some walking, hiking under the BPA power lines down south. And on a day that's damp, you could actually hear the bzzz. It's like, wow. Air is the insulator, and I guess it ain't working too good right now. Hope it doesn't arc to me. There's also a category of materials that are called semiconductors. Semiconductors are materials that can be altered to function as either a conductor or an insulator. Let me go back. I left out one thing here. Insulators are materials that have 5 or more electrons in the valence shell. 5 or more electrons in the valence shell. So conductors were 3 or fewer. Insulators, 5 or more. Anybody want to take a wild guess what a semiconductor might be? One that could be altered the function as either a conductor or an insulator. Anybody want to take a wild guess? 4. You all could have been scientists back in the 1940s. Because that's basically what they came to the conclusion. We know the properties of conductors. We know the properties of insulators. What happens if we start playing around with something that has 4 electrons in the valence shell? We could get it maybe to swing both ways, depending on how we want it to behave at that moment in time. And as you know, semiconductors are the fundamental building block of diodes and transistors. Transistors are the fundamental building block of computer microprocessors. That's all a microprocessor is. Now, in essence, billions of transistors on something the size of a postage stamp. Made of materials that have 4 electrons in the valence shell. Those materials that you're going to study later on in the program, not real important now for you to know, but I think you'll recognize one of the names. Germanium. That's not geraniums, that's what grows in the gardens. Germanium, it's an element. Carbon, that's an element. And the most prevalent, silicon. Silicon Valley. You've all heard of Silicon Valley? Have any of you know where Silicon Valley is? Have you ever been there? Vast mountains of silicon everywhere. No, it's fabrication facilities, labs. Okay? You're talking about in the Bay Area. Make sense? And what they did is they harnessed the power of semiconductors and made transformers, or transistors, excuse me, not transformers. That's another line. Trust me, we'll enjoy that lecture when we get to it. The other big thing I want to address with you is negative ion, positive ion. Because in essence, this is where voltage comes from. This is where voltage comes from. If I get this calculator here on the desktop, it's just been sitting on the desktop all day. It's just your average everyday calculator. I assume that since it was sitting on the desktop, minding its own business, it's electrically in a neutral, natural state. Because this calculator is made up of matter, which is made up of elements. Sitting here, neutral, natural state. So if I get this now, and I start rubbing it, what effect do you think that's going to have on the calculator? I'm cleaning it. No, it's a different class. That program's down the hall. Go out the double doors.
Creates friction.
Static electricity causes friction. The friction does what?
Creates charge.
How? And why?
Through the resistance of the fabric going across the plastic.
Close.
Somehow.
Close, kind of.
The difference of electrical potential, and then you're rubbing that cloth on the plastic calculator, which creates charge on there,
Mm-hmm.
and then when you touch it, you have less charge and the charge.
Yep, that's pretty good. It's pretty good. In essence, by me rubbing this and applying friction, which is a form of energy, when I apply energy to matter and I rub this, there's a pretty good chance that I am going to knock some subatomic particles. Which ones? Electrons off of what shell? Valence shell. If I rub this so hard that smoke starts coming out of it and it bursts into flames, chances are I've gone in too far. But if I just rub the valence shells and I knock some of those electrons from this onto this, now we've got a disparity. Now no longer, if I've removed electrons from something that was neutral, natural, and I've taken electrons from it, what is the predominant positive why?
Because electrons are negatively charged, taking them away leaves you with a positive charge.
Exactly. Now I'm left with more protons on this than I have electrons. It wasn't a neutral natural state, so I started rubbing it. Okay? So that's exactly what I've done. So I just made this a positive ion. I just made this a positive ion by removing electrons from it. If this was also in a neutral natural state till I started monkeying with it, now I rubbed electrons from the calculator onto the cloth. What does this mean for the cloth? It's now negatively charged. Why is that? Because it contains more electrons than it had when it was in its neutral natural state. Now, you know what? When I do this, both of these items, I don't want to make it sound like they have consciousness or whatever, but their whole freaking goal in life now is to get back into a neutral natural state. They cannot wait until I put them together and the electrons could jump off the cloth back onto the calculator and they could be at rest in a neutral natural state in a perfect world. Does that make sense? What I just shared with you is how we generate electricity. That's how we generate electricity. In order for us to generate electricity, we must apply energy to matter. When we apply enough energy to matter, we could knock electrons off the valence shell, gather them, and then say, hey, what? You want to get back to the you want to get back to the positive? Have I got a deal for you? Come, travel through my circuit, make this light bulb illuminate, and I'll give you a complete path back to your neutral natural state. That's what we end up doing as a career, making sure electrons that were harnessed are ready, able, and willing to do work for us, and then we make sure that they follow the correct path and do something for us. We just don't let them complete the path. If you're just letting them complete the path, that's called a short circuit. Okay? That's not a good thing. We'll talk more about that in future chapters. We just want to make sure that the electrons follow the path and complete that path. Make sense? Very critical. Talked about two big things already. The properties of materials we use in electronics, and also the property of how we create voltage or electricity. There's one other thing here the book does not go into. We have conductors, we have insulators, we have semiconductors. There's a fourth property that's floating around out there in science right now. Does anybody know what property I'm talking about? Superconductor. Very good. Very good. A superconductor, all of these materials, whether you're a conductor, whether you're an insulator, whether you're a semiconductor, you have one property associated with you. Everything has that property associated with it. It's a property of resistance. We're going to talk about it in a bit. There is a material that exists. It's called a superconductor. It has no resistance. The problem is, does anybody know where it exists? It is at low temperatures. So therefore, where it's going to exist is in a laboratory. They don't have it operating at room temperature. I can't bring you next door and give you a tour of my superconductor that I have set up over on a bench over here. Okay? I could if I had a cryogenics plant and I was, research facility and playing around with it. But when they harness superconductivity, it's really going to rewrite the textbooks on how we manage electricity and electronics. Okay? You think Bill Gates got a lot of money? The dude that captures and harnesses superconductivity at room temperature is going to be very, very wealthy. Very, very wealthy. Make sense? By the way, does anybody know what material they're having the best luck with as it pertains to superconductivity?
Graphene.
What's that?
Graphene.
Graphene, they're doing some stuff with that. But that's not the best results yet. Believe it or not, it is ceramic. Ceramic at room temperature is an insulator. It's a great insulator. We use it as an electrical insulator. But when they bring these ceramics to really, really cold extreme temperatures, they take on conductive properties and they conduct with no resistance. Pretty cool. Ionization, that's the process I just described. It's the process of gaining and losing electrons, and it's significant in current flow. Okay, without ionization, you wouldn't have voltage. Without voltage, you would not have current flow. Current, again, we should ring bells. Current is the movement of electrons from negatively charged atoms to positively charged atoms. The letter that we use to abbreviate current with is the capital letter I. Capital letter I. One of the terms we need to familiarize ourselves with when dealing with these electrical properties is the term coulomb. We'll talk more about the coulomb next chapter, but what a coulomb is 6.24 times 10 to the 18th electrons. This is a big, huge number. This is basically 6.24 and 16 zeros after that 4. It's too big to fit in your calculator. That's why we refer to it in this as an engineering notation. We'll talk more about engineering notation again in future chapters because we got to get you used to dealing with these extreme numbers. In electronics, we deal with a lot of extreme numbers. And we represent it with the capital letter C. Now, an ampere, named after André Marie Ampere, French physicist, 1 coulomb, that big number of electrons, 6.24 with 16 zeros after it, that number of electrons moving past a single point in 1 second is called the ampere. Have you all familiar with the term ampere before? If you've ever burnt out a fuse, you make sure you get the fuse that's the proper ampere rating. If you pop your circuit breaker, you need to make sure when you're resetting it that you're not overloading the circuit and exceeding the amperage rating of the circuit. And what that is physically a given number of electrons that you're forcing through a conductor in 1 second's time. 1 coulomb per second is 1 ampere. 15 coulombs per second is 15 amperes. We'll talk again more next chapter on that. Current's measured in amperes and it's represented by the capital letter A. So if you go out to your fuse box in your car, pull a fuse out, and it says 15A next to it, that stands for 15 amps. Universally accepted. Universally accepted. Potential, the ability of a source to perform electrical work. What we're talking about here with potential is voltage. Difference in potential causes electrons to move or flow in a circuit. This is referred to as EMF, or electromotive force, or voltage. EMF, electromotive force, voltage, difference in potential, they're all synonymous. Voltage, ring bells, chimes, hit the gong, is the force that moves electrons in the circuit. It's the pressure or pump that moves electrons, represented by the capital letter E or the capital letter V. Whether you use E or V, here the textbook uses E, you could use V if you want, as long as you know what we're talking about. It's universally accepted. The unit of measure is called the volt. Resistance, the opposition to the flow of electrons. The degree of resistance depends on size, shape, and temperature, and it's measured in ohms. Named after George Simon Ohm, represented by the Greek letter omega. One of the things I want you to familiarize yourself with is, you know what has resistance? Everything. Everything, except superconductors. And superconductors only exist in a laboratory right now. Hopefully when you buy an extension cord, that extension cord has a low amount of resistance. Okay? Hopefully when you buy new spark plug wires for your car and they're insulated, hopefully the outside of the spark plug wires has a high amount of resistance. Make sense? Conductors have low resistance to current flow. That's why they're called conductors. They have many free electrons to transfer the energy. Insulators have high resistance to current flow, very few electrons. In summary, tonight we talked about matter, we talked about elements, the fundamental building block in nature, we talked about atomic structure, specifically subatomic particles and a place. Right? Nucleus is not a particle, it's a place. which that place contains the protons, the neutrons, and the electrons. Protons are positively charged, neutrons are neutrally charged, and electrons, well, those are the other ones, they're negatively charged. We talked about atomic number of protons in an atom, atomic weight, number of protons, and number of neutrons in an atom. We talked about shell. These are the orbital arrangements of the electrons, starting with the K shell, going all the way up to the Q shell. We talked about ionization, the process of taking things out of a neutral natural state. We talked about current. Current is the flow of electrons from negative to positive. Why? Because it wants to get back into a neutral natural state. We talked about the Coulomb, 6.24 times 10 to the 18th electrons. It's a number of electrons, like a dozen eggs, a bushel of apples, a gallon of gasoline. We talked about the ampere. The ampere is 1 coulomb per second. We talked about electric current that is measured in the ampere. And then finally we talked about potential or electromotive force. What we're talking about there is difference in potential or voltage. Does anybody have any questions on anything that I covered in a lecture for Chapter 1? Going once. Going twice.
This will be on the website there, right?
What's that?
This will be on the website, right?
Yes, these slides are on the website. The audio recording is on the website, and eventually we're going to get the video uploaded as well. But the content will remain the same.
Yes. It'll be the new Google site.
New Google site. Any other questions? Going once, going twice, going. The new Google site, the last one that's listed there, the HTTPS, sites google.com, site LWTC Electronics. I've got that turned on to anybody with the address should be able to get in there. We haven't uploaded this material to it yet, but should be there.
Take the S off for it to work, don't you?
Really?
Yeah, because I think the S means that there's somebody with administrator access logged in on a secure connection.
So like messed up? Is that what you're saying?
Yeah.
All right, I messed up.
I think so.
Cool.
I don't have scientific evidence.
Cool. That's why you got the job as TA. You're here to keep me honest. Any other questions? Once, twice?
I should know where lead falls in that conductivity.
I honestly don't know. I mean, it's pretty far down. It is a conductor, of course.
I think it's amazingly good.
It's real close on a periodic table. It's amazingly close to silver.
Yeah.
It is good, but it
Oh, yeah.
collects, you know what I mean?
And that's why actually in solder we used to contain lead, but because lead is lead and it's bad, they realized it was really, really bad, so we pulled it out of solder, but it was used to join in complete electrical circuits, so it's pretty high. I don't know its actual conductivity value, but it's pretty high. Going once, going twice, going, gone. We're black. The next questions that I have for ELEC 110, Chapter 1, you'll be answering for me on a quiz. But don't worry, well, you'll have another week or so before we take the quiz. I'll coordinate with the class lead on that. Any other questions about protocol, anything else we're doing here? All right, I'm going to go ahead and cut you loose. We don't